Okay, welcome back everyone to the problem involving two particles, one on a table and one hanging vertically from a pulley. Okay, so at that point we have B will have reached that position here on the ground, and A will have moved to about here. So there's your A and there's your new B. And A will have moved the same distance as B, 0.5 meters. So at that point though, A then loses the force of the tension in the string, because the string has gone slack, so it's no longer pulling A. So that means the acceleration is now changed. The situation is now changed. We should now draw a new diagram. So here is A on the table, and there's no longer the tension there. So we just put on the forces that are acting on A now. We have still got the resistance force, and that's constant, 0.8 G. And that's all horizontally. Obviously we still have the reaction and the weight, although they are vertical and not part of the motion. So now we need to find the new acceleration. So let's call the new acceleration, let's call the acceleration A dashed. Okay, so now we're going to apply Newton's law again, resolving horizontally in that direction. The only force is the resistance, which is in the opposite direction, 0.08 G, so that's minus 0.08 G, and that equals MA. So 0.4 is M, A dashed is our new acceleration. So we can see that A dashed is minus 0.08 G over 0.4, and that equals so 8 over 40 minus G over 5. So now we need to find how far A moves before it comes to rest. We have the new acceleration, it's constant, so as we always do with constant acceleration, we use SUVAT. Let's write down the new values. We're looking for S, we're looking for the displacement. The initial velocity was, if we remember, that's right, 7 over 5 root 3. So we have 7 over 5 root 3. And then we need to know when it gets to rest. So the final velocity V is 0. A we've just found is minus G over 5. And we're not interested in the time. So if we're not interested in the time, the equation to use is V squared is U squared plus 2AS. So we have 0 equals U squared, which is 49 over 5 times 3, squaring 7 over 5 root 3, plus 2AS, so it would be minus 2 over 2G over 5, so minus 2 over 5G times S. So G is, of course, 9.8, so that's 2 over 5 times 9.8 is 49 over 2. Beg your pardon, 49 over 5. And that equals, S equals 49 over 5 times 3. So the 49 over 5 cancel, and we have, it looks like S equals 2 over 15. No, I've made a mistake there. U squared was 49 over 25 times 3. So we have 25 here. So dividing by 49 over 5. Oh, wait a minute. So that will be 2 times 49 over 25. So dividing by, we get 2s equals 3. Okay, so s equals 1.5. So the displacement of A and is 1.5 meters. That would be the distance moved before it comes to rest. So A will be moving somewhere over here, and that is 1.5. If you remember the original question had the distance from A to the pulley as 4.5. So we can see it's moved 0.5 whilst it's under tension from the string, and then a further 1.5 before it comes to rest, which is a total distance of 2 meters, which is less than the 4.5. So we know that it doesn't hit the pulley before it comes to rest, as it could have done. So we could write the total distance moved by A equals 0.5 plus 1.5 is 2 meters. Okay, so that's how to solve problems where you have a particle on the table connected to a particle hanging over the side of the table and connected by a string over a pulley. Now, there are 2 questions in the book that you can try that involves a similar situation. That is number 5 in exercise 10F. On page 177, and exercise, the mixed exercise after that, mixed exercise 10, number 14. Number 14 also has a similar question. So maybe you might like to go and try those 2.